Hey everyone, thanks for attending my presentation. My name is Asmam Gabriel and I'm a PhD student at NTT University. Today I'm going to talk about my research topic, deep learning for flood extent mapping. As you know, floods are one of the leading cause of deaths from natural disasters in the United States. So developing a model that automatically extracts flooded area from either UAV or satellite images uh, uh, is essential to support flood emergency response and as well as to provide uh, flood assessment. So in this study, we use deep learning to automatically extract the water parts from your image. Deep learning is one of the machine learning techniques that teaches computer to do what comes naturally humans do. So, as we see the images, we can recognize what features the images have. For example, we can see there is a road, building, vegetation, right? But the computer sees that pixel array. The computer doesn't recognize what features the images have. So in this study, we develop a model, then we train with using UAV images, then using tests the model, that after that the model can automatically extract flooded area or building, highways, roads, everything. We can use different types of images. So deep learning has 3 layers: input layer, multiple hidden layer, and output layer. Input layer means, in our case, images is our input layer. Output layers means what we need to have. Like in this case, for example, we label our images into 4 classes: water, we have building, road, and vegetation, right? So that's our output will be. So deep learning is a key technology behind autonomous cars. For example, in autonomous cars, they teach the models to recognize while driving in the street. For example, traffic signs, poles, pedestrian, everything they train. And once the model trained, so it can recognize those objects. So here, I just want to talk to you about what's deep learning architecture. So hidden layers, deep learning has multiple hidden layers. One is feature extractor layers. We call it convolutional layer. There is downsampling layer. There is probability prediction layers. Those layers together form deep learning architecture. So if you train that architecture, we can create our models. So there are different popular deep learning models nowadays. AlexNet is developed by Alex Kirkowski. So GoogleNet, VGG60, those deep learning, those models differ from one another based on their architecture. For example, AlexNet has 22 layers, like feature extractor layer, downsampling layer. GoogleNet has 22 layers, VG has 60 layers. So AlexNet trained to recognize 1,000 objects like pen, pencil, computer, person, something like that. All of them also trained for. So AlexNet achieves 87% accuracy. The second one achieving 92. The third one also 90 point something. When we say 92% accuracy means, for example, we can see here 92 means, for example, we train to recognize a person, but if it says horses as a person, there is error, right? That's what we say accuracy. So deep learning has different application for object detection and recognition. For example, it can use for face detection. If I train your pictures once, so if you guys have different images, so it can automatically extract individual's photo, something like that. It can use for agricultural purpose to recognize unhealthy crops, something like that from healthy crops. It can use for remote sensing application also to extract roads, buildings, something like that. So in this study, we investigate the potential of deep learning method for extracting flooded areas. Our motivation for this project because most of studies uses deep learning and they achieve outstanding results. But for remote sensing, a lot of researchers are not applying this to extract flooded image. They use like traditional approaches, support vector machine, random forest, something like that. Still, we are working on that. So in this study, we use two types of data. The one that we get during Hurricane Matthew, the data is collected over Prince Village. The others during Hurricane Florence in Lumberton and Fairfield. So this data is collected by North Carolina Emergency Management. So what we did here, we didn't develop a model. There is a model already, VGG. So those models are used to extract features like pen, pencil, not for remote sensing applications. So what we did, this is, for example, VGG model. It has 16 feature extraction, certain feature extraction layers and 3 final layers. So to develop a model to train from starting from scratch, so we need to have million images, like 2 million, maybe 100 million images to form a model that can learn like automatically. So what we did, we have small images, small amount of image, like 100 images. So we do fine tuning. Fine tuning means we keep the first 13 layers that is used to detect corner, like edges. So we keep that layers and we change the last 3 layers. This okay, you see the one in the blue? The last layer is, I'm sorry. Here, we see 1,000, right? So these 3 layers used to give us like 1D map. 1D map links with 1,000. For example, our images have pen, pencil, book, something like this. Five features. So we will get 5 classification, like pen, this is pen, this is pencil, something like that. For remote sensing, we need a map, like thematic map. So we change those layers, 3 layers for our application. So we get something like this. So we'll have here something, right? So in this case, we can classify our images for class like building, water, vegetation, and road, right? So we have here for that picture. So when we will have this input, we will get something like this output. So our approach consists of the labeling, training, and classification stage. So we use 100 images, we label all 100 images, something like that. Here is an example of labels. So we label, this is water, this is vegetation, this is building. So this, we call it training image. So we have like 100 training images and 100 corresponding labeling images. So when we feed to the computer learns. This thing is vegetation, this thing is building, something like that. The other thing, we have testing images to test our accuracy. This is different from, this is not involved in the training, like testing images. So we have like 50 testing images, so we label them because the labeling part is for as a reference. For example, after I develop the model, I use that image for testing, right? So it automatically extracts, right? So I need to have label image to compare whether it's extract correctly or not. for validating. So here is the general pipeline of our approach. We have training, classification, and testing stages. So in the training stage, we feed the computer all 100 images and its corresponding ground truth level. So in this study also we train another model, FCN8S classifier. This model is different from the one that we have based on the number of their layers. We also train SVM, support vector machine classifier. It's traditional approach. It's not actually deep learning different from the traditional approach because deep learning can automatically extract images, features from images. When we use traditional, we need to change like Excel form, something table, then it takes some time also. So here is our result, for example. The first one is test images. The second one is what we label manually using MATLAB. The third one is what we segmented. Like, you see here, for example, here, this is building, this is road, right? The building, something here. There are also another images here. We can see here. The blue part is water. This is test image. In deep learning, like if you have trillion images, once we can in folder, it automatically put the image into the network. So if you want setup, we don't need to touch like something like that. For training also, it takes 3 days to train this network. Once I set up the code, it automatically takes images and trains the network. Here is another one, for example. Also, we have quantitative results. For example, you can see here. The one on the left side is the reference value, the one that we labeled. The one in the upper, this one is the reference value, this one is the one segmented. So when we see the first line, 97% means 97% of the images accurately classified as a water, 1.3 is misclassified as a building, 1.2 as a vegetation, as a road, something like that. So we compare our classification result with other methods. With SVM, for example, SVM achieves 87 on overall accuracy. Our approach achieves 95%. Actually, here our objective is only to extract water parts, not vegetation, building, something like that. We can classify our images like flooded, non-flooded. But here we classify in 4 parts because we want to see how our model classify roads, buildings, something like that. But if somebody who works to classify vegetation, for example, lower vegetation, high vegetation, or something like that, we can use these models. But one thing here, we use here our data here in principally Lamberton fair problem. For example, if there is flooding happen next year, we can use these models in this area. But we can't use this in Arizona. For example, in Arizona, vegetation, there is a different types of vegetation. So deep learning is supervised learning. If you teach something, it will learn. But if you didn't teach that things, it doesn't know. So in this area, one of the problems to use this model in the whole North Carolina, because in this case, building means we see the top part of the building, right? When you see building means because aerial images, right? So different building have different roof size for roof colors because we are doing here semantic segmentation, right? Maybe some roof is similar to water or build vegetation, so it's difficult to differentiate. So here is our classification accuracy for each classes for water, building, for those 3 models. So thank you if you have any questions. Test images? Yeah, for fine tuning, 100 to 100, that's fine. But if you wanna develop a model by itself starting from scratch, you need to have million images, like 2 million, 3 million, maybe more. So if you train with that amount of image, you will create a model that can automatically detect or recognize objects. But with 100 or 1,000 images, you can't do that. But there is already pre-developed models by computer scientists for, actually they developed this for autonomous cars. Autonomous cars work by using this approaches, like deep learning can recognize objects around the street, and they use also LiDAR to measure the distance between the car and the object, something like that. They are working on that. But in remote sensing, we don't have background for computer science, right? So we are working on a remote sensing area. But they didn't know. People from computer science, they didn't know what's our problem in detail. That's why I'm working on this approach. I'm learning how to, yeah. So my contribution here is I use pre-trained model. I change the last layers. For example, if I use that model to test our images, it didn't give me nothing because the model trained to classify 1,000 images, pen, pencil, something like that, not for aerial images. It's 1D, like its segment is 1D. For our image, we need 2D map, like so. Here, so we need also upsampling. Upsampling means it go to downsample, right? To 4 classes like pixels. So we need to create a map. So we need to add upsampling layers.
When you actually are creating your layers to train, are you actually digitizing out polygons to separate out to create classification types for your different layers? How do you actually differentiate between, say, I saw one image of vegetation and water, or are you just creating polygons?
Yeah, polygon, like we label manually, like we create polygon, like we label all pixels. For example, vegetations, we label all pixels on vegetations, building everything like that. So once,
how long did that take you
for labeling?
Yeah.
For me, actually, like because I'm working research, I'm a PhD student. I don't want to finish like once. If I need to finish in one day, I can actually. But for my research, I was doing like maybe months or something like that. Yeah. But there is also algorithm that automatically label your images. If you pay, there is also library for that purpose.
What the information did you use? Use UAV images, right?
Yeah, UAV images.
So did you use only color, or did you also use some information about the elevation?
I use not here only 2D maps, like not elevation. So it only recognize the area, right? So we can integrate this with elevation maps. For example, you can develop elevation maps, right? And reference maps. So this helps us which part is flooded area, which is not. For example, for emergency responses. So it's difficult to recognize which part is affected by flood, which part is not, right? So the UAV only takes images around. So we use that for only 2D, like to know the area, not elevation. So also this can also use for, if you have time series data, we can predict flood, like temperature, flood, something like that. But we need to have time series, like 400 images. How was, for example, if you have data about Prince Village, and if there is flood before in years 400 images, how was the level of the flood, something like that. So it can predict also. We can use for that application. Where what? Actually, it's already the image is already collected. I have image, but we can use like for live. For example, when the UAV collect data, if you can connect with Bluetooth, or if you occupy this model with a UAV, so we can automatically extract. While UAV taking images, then automatically can extract the flooded area. But here we have already images collected by North Carolina Flood Emergency Department. You see program? What type of program you say? Communication means, when you say communication?
What type of computer? Your desktop?
I use my laptop actually. For training, we need to have high GPU computer. For example, Google has that, right? If I need to train like 100 million images, I can train with my laptop or something like that. That's why it's, yeah. GPU. Yeah, I use GPU. Yeah. Any other question?
It's more like a personal curiosity. So you have water classes, the water building, vegetation.
Yeah.
Why didn't you include like an impervious surfaces or like dirt, or was that like a thought at any point?
What?
Oh, so if there was like dirt in the image, is that classified as vegetation? It's just like ground.
Dark, yeah. Here, dark, I didn't include darks actually, because there is dark in vegetation. There is also dark in the water part, you know? So if I include dark, so the water will be classified as a dark. That's my future research. Yeah, I'm working on that to classify. Actually, I tried to classify that, but as you see here, yeah, here is, you see dark? Because in our image, most of the dark parts are on vegetation. So even there is dark in the flooded part, in the water part, so it's classified as vegetation. Yeah. So that will be my future work. Any other question?
Do you know of any open source AI tools for GIS that are developed or being developed?
Okay, I will talk to you later. I will see if I can. Yeah, yeah.
It's been a while since I worked on image classification. There was a program I worked in grad school, Paradise Magic.
Yeah.
It does classify an image into a category.
Yeah.
How different is this from
This one?
traditional
Yeah.
classification?
One thing, it automatically extracts features. Like once you set up, it automatically learns from images. The traditional one doesn't do that. That's one of the other thing. It's accuracy also. We can achieve high accuracy. Still, they are working on this. For example, in 2012, they achieved like 60% accuracy. You see, now it's 99 something. So we'll have 100% in the near future, 100% accuracy. For autonomous car, we need to have 100% accuracy, right? Uber tried last year autonomous car, right? So it killed 1%. Because it's still there need to work more research. It should be perfect. Sometimes it's hard to recognize like similar objects. We can recognize a car, right? A laptop. We can recognize a car which is involved in accident, right? But when we train the network, we only train the car. But it's involved in accident, something like deformed. The network will not be identified. There is a lot of challenges. Yeah, still need to work on them. Any other question? All right, thank you very much.
Good, thank you.